Today we are going to talk about the topic of indexes and scientific notations. First of all, we have already learned about the like terms and unlike terms, which are essential in the addition and subtraction of algebra. But for multiplication, basically even if the terms are unlike terms, we can still multiply them and simplify them. For example, in this question, the numbers, of course, we group them together. And then for the algebra part, we see that p and p squared are actually unlike terms, but we can simplify them by adding the index together, giving this p to the power 3. And q cubed are also unlike terms. And we can add the indexes together, giving rise to q to the power 4. So you can see the difference that in addition or subtraction, basically p and p squared, we cannot simplify them because they are unlike terms. But in multiplication, we can just add the indexes together and making it become one term. And in example 2, similarly, we first can multiply the coefficients together first. And then for the algebra part, you see that there's 3p. Even though they are like terms, in addition we will say p plus p plus p is 3p. But if it is multiplication, 3p multiplied together giving rise to p to the power 3, or p cubed. Which means we add the indexes, each of them have an index of 1. We add the indexes together. Q as well. Q to the power 1, which is invisible, plus the index of q squared is 2, giving rise to q cubed. This is the way how we deal with multiplication of algebra with indexes. And another example, bear in mind that the previous example we don't have a bracket and an index outside. But if we have a bracket with an index outside, which means every member inside the bracket we need to multiply with that index. For example, AB all cubed means A cubed and B cubed. And this part as well, we need to multiply the 2 with 2, 3 with 2. So it gives A to the power 4 and B to the power 6. So altogether, it gives rise to this expression. And for the index part again, for same letter of algebra, we can add the index together. So it's 3 plus 4. Here is 3 plus 6. So it's A to the power 7 and B to the power 9. And for division, the same. We should bear in mind that for algebra with the same letter, when we divide them, it's always the letter on the numerator and the letter on the denominator, the index would minus each other. So let's say a to the power 6 divided by a to the power 4 is 6 minus 4, and b to the power 2 and b to the power 4 is 2 minus 4. So it gives rise to the item on the lower part. We can then look at example 6 here. We can see that outside the bracket is a minus 3 index here and minus 2 index, which means every member inside the bracket needs to time the index outside. So it would give rise to this sentence. 3 cubed x, 2 times minus 3 is x to the power minus 6, y to the power minus 3, and so forth, 9 to the power negative 2. X, originally it has power 3. 3 times minus 2 is minus 6. So there are x minus 6 and y minus 6 as the two terms. And then for division, basically we can apply the addition and subtraction of index to tackle this problem. Like, we can mentally think about x to the power minus 6 divided by x to the power minus 6. Actually, the index is minus 6 minus negative 6. That means it cancels each other. So this item will be omitted, is crossed out. And the item y to the power minus 3 divided by y to the power minus 6 is minus 3 minus negative 6. So it will give rise to a power of 3. So it's y to the power 3. And so forth. 3 cubed means 27, and then 9 to the power minus 2. If we use a calculator, or we can do it with a draft, it would give us this number, 21x7. So altogether, this is the final answer, and this is the way how we tackle indexes outside the bracket. Each item needs to have a relationship with the index outside. There are some similar expressions as well. And another topic is about scientific notation. So if we have a times 10 to the power n, or we should say when we express so-called scientific notation, there is a rule to follow. It should be expressed in a times 10 to the power n. And it would mean the a should be within a single-digit integer. So it should be a positive integer and within 10, and should be single digit, so it should be any number between 1 and 9, smaller than 10. So let's take a practical example. Let's say if we have this item and we need to express it in scientific notation. First, we can make both numbers in a scientific notation first. This one should be 5.2, and then there are 1, 2, 3, 4, 5 places afterwards. So it would be 5.2 times 10 to the power 5. And then here, if we count from the first digit, 8, and 8, there are 3 places before it. So it would be 8.5 times 10 to the power minus 3. And the interesting thing is that actually we will discover, according to what we learned about law of indexes, for algebra of the same letter or the same number, we can, when we have same number to different powers, we can actually add the indexes together when we multiply them. So it means 10 to the power 5 times 10 to the power minus 3, we can group them together, and 5 plus minus 3 gives 2. And another part is the 5.2 and 8.5, when we multiply them, just gives another number. And then we rearrange everything. It would be 4.42 times 10 to the power 3. So let's say before, the point is over here, we need to move the point 2 places afterwards in order to get the exact number. Now, we change it into the point after 1 digit, so it means we need to move 3 places after it to give the same number. And so forth. Similar example, we would group the 10 together first and add the indexes together. It gives rise to 10 to the power 19. And this part also, if it gives rise to a single digit, we don't need to rearrange. And then here, we can take a look at example 4. We can see that 7.74 times 10 to the power 26, and the lower part is 2.58 times 10 to the power 9. Basically, we can already categorize 10 to the power 26 and 10 to the power 9 of one group, because we can easily subtract both of the indexes. So we can group that this item divided by this item, and 7.74 divided by 2.58. Again, we can rearrange the decimal points afterwards. So for this bracket, we can see that we can simply use 26 to minus 9. This gives rise to power 17. So finally, we get this answer, 3 times 10 to the power 17. And if we go back to look at example 3, basically this example 4 and example 3, we deal with the 10 to the power something items with two different approaches. One is that for 10 to the power minus 7 times 10 to the power minus 3, we can add the indexes together. But for this part, we should subtract the indexes. So here is also easy. 10 to the power minus 7. Here we add minus 7 and minus 3, giving rise to minus 10 as the index. And we can see here, because the blue items, after multiplication, they give rise to 15.33, which is not accurately scientific notation, because there's a rule that before the decimal point we should have only one digit. That's why we will rearrange the decimal points by considering how to adjust the power after the 10. So let's say we can imagine that 15.33 originally here minus 10 power means we need to move the decimal place forward for 10 places. And now if we need to make it into, the point is just after 1, which means we still need to move forward for 9 places to get to the same position. That's why when we rearrange, we can see that it should be 1.533 times 10 to the power minus 9, because before is moving 10 steps before, and now we have already moved 1 step before. So only 9 steps are left. And that is the final answer.